Marhaba. Okay, so we are still studying functions, and today we want to learn about an operation we apply to functions, which means suppose we have two functions, g and f, and we will create a new function called the composition of these two functions. So let me start by a diagram to explain what we will do. Suppose we have a function g from a to b. Okay, so suppose this is the function g, and whose domain is a and codomain is b. And suppose we have another function f from b to c. Okay, so this is the function f from b to c. So what happens here, suppose we choose an element here, then the function g will send it to some element in b, and this element is called g of a, right? And now, since g of a is in the domain of f, then f has to assign an image to it in c. And so this is the element. What is this element? It's an element in c, and it's f of g of a, right? F of g of a. Okay. This means that for every element in a, we assigned some element in c, and this is a function, right? What is a function? It's an assignment which assigns to every element in the first set some element in the second set. So here we get an assignment. Okay, we will call it f after g. So this small circle is read as after, or if you want, we compose f after g. Okay, so once we have a function g from a to b and the function f from b to c, we can define or construct a function from a to c, which we call the composition of f after g. So let me write this properly. Okay, so suppose g is a function from a to b, and f is a function from b to c. Okay, then the composition okay, of f let me say after g is the function. What function is it? It is the function denoted by f after g, and it has domain a and codomain c given by say, let's choose an element in the domain a. Its image under this new function, which we denote by f circle g, is first we apply g to a and get its image g of a, and then we apply f. Okay, so f after g of a is this element. It's f of g of a. And what's f of g of a? It's following this picture. So we start with a, we apply g first, we get g of a, an element in b, and then we apply f to this g of a to get an element in c, which is f of g of a. Okay, so this is the composition of two functions, f after g. Okay, let's have an example. Okay, suppose in the first set we have a, b, and c, and in the second set we have also a, b, and c, and this is the function g, and g maps a to b, b to c, and c to a. Okay, now suppose we have another function f whose domain is ABC and codomain is 1 to 3, the set containing 1 to 3, this is f, and it maps A to 3, okay, B to 2, and C to 1. So we have these two functions, g and f, and now we want to compute what is f of g of a, say. Okay, so what is f of g? F after g is a function. Let's call this set a, this set b, and this set c. Then it will be a function from a to c. Now a contains the elements a, b, and c contains the elements 1, 2, and 3. But look, what is the image of a under this new function? What is the function f after g? Which means first apply g, and after this apply f. So apply g to a, you get b, and then after this apply f, so you get 2. So we know that the image of a under this function is 2. Now let's see what is the image of the new function of b under the new function. What is the new function? First apply g, and then after this apply f. So b, apply to it g, you get c, and then apply f, you get 1. So b goes to 1. And now look at c. C, apply g to it, you get a, and apply f to it, you get 3. So c goes to 3. Okay, so this is the composition. This is a new function, which is the composition of f after g. Now, if you want to use the formula of in which we define the composition, then we get the same answer. So, for example, f of g applied to a, by definition, it's f of g of a, which means apply g to a first and then apply f to the result. So this is f, but what is g of a? Look, g of a is b, right? So this is f of b. And what's f of b? Here is f, here is b, f of b is 2. Okay. See, this means f of g of a is 2, which is this f, the image of a is 2 under the composition. Similarly, if you want to do f of g of b, then this is f of g of b, but what is g of b? It is, right, g of b is c, so this is f of c, and what is f of c? It is 1. Okay, f of c is 1, and so the image of b under this function is 1. So this is the composition of two functions. Let's take another example. Okay, let's consider the function f from the natural numbers to the natural numbers, where f is given by f of n is equal to 2n plus 3. So f takes an integer and produces twice the integer plus 3. And g is another function from n to n, where g of n is equal to 3n plus 2. Let's compute f after g of n. So f after g, this function, we compose f with after g, and we want to see what is the image of a natural number under this composition. Okay, what is this? This means first apply g to n, and then apply f to the result. Okay, f, what's g of n? It's 3n plus 2. And what's f of 3n plus 2? Look, what does f do to the input? It multiplies it by 2 and add 3. So it will be 2 times the input, which is 3n plus 2 plus 3. So this is 6n plus 7. Okay, so this is the function. It takes, this is the composition of f after g. It takes a natural number n as an input and produces 6n plus 7 as an output. Okay, let's compose them in the other order. So g of f of n. What is this function? This means apply g after you apply f. So first apply f of n and then apply g of n. So this is g of f of n. What is f of n? It's 2n plus 3. Okay, and now what's g of 2n plus 3? This is what the function g does, it multiplies the input by 3 and adds 2. So multiply the input by 3, the input is 2n plus 3, and then adds 2. And so this is 6n plus 11. Okay. And for example, what's the image of 2 under this function? This means f of g of 2, which means first apply g to 2. What happens if you apply g to 2? What's 2 times 3, 6 plus 2 is 8. So this is f of 8. And what is f of 8? F of 8 is 8 times 2, which is 16, plus 3 is 90. Okay. You can check now. F after g of 2 is 6 times 2, 12, plus 7 is 90. Okay. So this is the composition of functions. Let's have another example. So another example, let f be a function from the set of real numbers to the set of non-negative real numbers, okay, where f of x is equal to x squared, and g is a function from non-negative real numbers to the real numbers, okay, where g of x, so the image of x under g is the square root of x. And notice here, we need the domain to be non-negative real numbers, otherwise we can't compute the square root of a negative number. Okay, so let's compute what is f after g. This is a function whose domain is the domain of g, right? Because we first apply g. And codomain is the codomain of f, which is also the non-negative real numbers. Okay, let me just go to the first diagram above. Notice here, let me use the red. So what is the domain of f after g of this new function? It is a, and the codomain of f after g is c, right? This function assigns an image to any element here, and the image belongs to c. So the codomain of c, but what is the range of f after g? Okay, what is the range? It's the set of images of these functions. But what are the images? They are the images of the images of. Okay, so they are the images under f of the images under g. So this means that the range is, so first, this is the set of, let me, for example, start here with a, and then, or any element in a, and then take all the images in b. So this is what, if you take all the images, this is the range of g. So this is g of a, the range of g, and then we apply f to this set. So this set is the set of all images of g, then we apply f to it, and we get, I know it's not clear, but we get, this will be the range of the composition. So this is f of g of a. And in words, it is the image under f of the image of the domain of g, which is the range of. Okay, let me say it again. The range of f after g is the image under f of the range of g, right? G of a is the range of g. Now, what do I want to say? Let's get back to our example. And so we have two functions, f and g. F is the square function, g is the square root function. Now we want to see what is the composition. It's a function from non-negative real numbers to non-negative real numbers. So f after g means first start with g. So we start with the domain, we apply g, and then we apply f. So maybe we Okay, we apply G, right? This is G, and then from G we apply F. So you see that this is the domain of the composition, and this is the codomain of the composition. Which composition? F after G, which means apply G, and after this apply F. So let's see what is the image of a single element. By definition, this is F of G of X. If we first apply G to X, we get square root of X, and then apply F to this, we get square root of X squared, and this is X. So this means that F of G of X is X. Do you recall what is this function? This is called the identity function on this set. Remember, the identity function on a set, it takes an element and produces the same element. So it takes X and produces X. Okay, I hope this, remember that these were inverse functions from, like, the inverse of X squared is square root of X from the previous session. So this observation is true in general, by the way. So let's say it. So suppose, let me explain what do I mean. Suppose F is a function from A to B, and this function is a bijection. We've seen that if you are given a bijection, then the inverse exists. The inverse of F inverse will be a function from B to A, and it exists. Why? Because for every element in B there is a unique pre-image in A, and this defines an assignment from B to A. So here is the picture. Okay, so we have A, we apply F to B, and then you apply F inverse again from B to A. So let's compose F inverse composed with F. Okay, and this will be a function. So first apply F. So the domain is A, right? To apply F, we need to start from A, and then apply F inverse. So you will end at A as well. And so let's see what is F inverse composed with F applied to A. This is F inverse of F of A. So if this is A, then this is F of A. But we know F inverse of F of A is A. So, I mean, if we call this element B, then F of A is B, and we define if so if and only if F inverse of B is A. So we define the inverse function in this way, right? This is the element A, this is the element B. B is the image of A under F, and we define the image of B under F inverse to be this A. Okay, so this means that F inverse of what is F of B is B, but we defined F inverse of B to be this A. Okay, this means that the composition F inverse after F of A is A itself. So this means that the composition is the identity function on the set A. Right? It takes A and produces A. Now let's see what happens when we compose it in the other order. So F after F inverse. So let's use a different color. Let's see what's F composed with F inverse. Look, this means we need to start with f inverse, and after this we apply f. So to start with f inverse, we need to start with b from an element in B. So start with an element in B, apply f inverse, we get A, and then apply f again, so we end in B. So this means this is a function whose domain is B and codomain is B as well. Now, so let's choose an element B in B. Let's see what's the image under this composition. So f after f inverse of B is f of f inverse of B. But what is f inverse of B? F inverse of B is the element A whose image is B. So it's f of A, but we know what is A. A is the element whose image is B. Okay, this means that f composed with f inverse of B is B itself. So this new function, the composition of f after the inverse of f, takes an element B and produces the same element. And so this shows that f after f inverse is the identity function on the set B.